Yeah.
See if this works. Fine. This,
So it's not in full screen mode.
I know, and normally it should, if I do Control L, it's supposed to, there we go.
Yeah, perfect. Got it.
Yeah, that's fine.
Yeah.
We do like to ask questions as we go along, so
Yeah,
hopefully
so
that's-
I encourage it, please.
Fantastic.
I even have some backup slides in case they turn out to be useful, but okay.
Perfect. Okay, well, let's get started. Thank you so much, everyone, and nice evening or morning, whatever time zone you're in. It is my absolute pleasure to introduce today's speaker, Howie Haber, who is a distinguished professor in, well, particle physics, in collider phenomenology, in SUSY, and he's done a lot of work in the field of scalar extensions, for example, the 2x doubler model. And I usually joke saying that the 2H in 2HDM stands for Howie Haber, because yeah, everybody who knows 2HDMs knows Howie. And it's my honor to introduce him as a speaker today, and I give the virtual floor to you, Howie.
Okay, thank you very much. It's a real pleasure to be able to give this talk, and I only wish I could be visiting, because in fact, even though I've been to in the vicinity, namely to the UK many, many times, I've yet to be able to visit Ireland, and something I've always wanted to do. So hopefully that opportunity will come in the not too distant future. So I'm going to try to explain why the Higgs boson that has discovered almost 10 years ago now at CERN seems to be so much resembling the particle that was predicted by Higgs back in 1964. Of course, he didn't predict the version quite that we see experimentally, but nevertheless, it's experimentally very close to what it is theoretically in the standard model. And so I'll review some of the experimental evidence for that and discuss why that might be the case. Let's see. What's the best way to... okay. So my quick outline. The Large Hadron Collider has revealed a standard model like Higgs boson. And well, there are many reasons to think that that's not the whole story. And I'll be considering non-minimal extended Higgs sectors in this talk. And if you're going to consider such possibilities, then you have to have some understanding of why the experimental object behaves so much like the standard model version. At the end of the day, maybe it's just an accident, but physicists usually prefer to find a reason behind such accidents, and often they involve symmetries. So this will bring me to the discussion of symmetries and extended Higgs sectors, and the 2x doublet model, of which this is the acronym, will provide a good example of the phenomenon I want to talk about. Now the symmetry is not going to be exact, and so the hope is that if it's an approximate symmetry, you will eventually find deviations in the experimental data that will hint of what lies beyond the standard model. Turns out this works incredibly well if you ignore the couplings of the Higgs boson to the fermions, the so-called Yukawa sector. And so that's going to present a little challenge, and I'll discuss one possible approach to that towards the end. So this talk is based on primarily 2 different papers that came out last year, and those are the citations. So, standard model like Higgs boson. So here's some data. There are 2 main experimental collaborations at the Large Hadron Collider, ATLAS and CMS. And to give, not to favor one over the other, I'll show you 2 slides. This one from ATLAS collects a lot of different observations of Higgs physics. Some of it involves the production mechanism. So you see here, GGF stands for gluon fusion. That's the main production mechanism for producing Higgs bosons at a hadron machine. And then this column here tells you the signal that was actually seen. So this is the Higgs boson has been produced and decays into 2 photons, 2 Z's, 2 W's. When I say 2 Z's, it turns out one of them is virtual, one of them is real. And in this particular case, the 2 Z's end up as lepton pairs. So the final state here is 4 leptons, say.
So just an aside and what a question that somewhat related, if I may. The recent data on the W boson and potential discrepancy there, would it have an impact on these or what? Well, maybe what is your opinion on that and what impact would that?
Yeah, boy. No, well, it doesn't change any of the numbers here. Of course, it could be a hint for new physics beyond the standard model. And, you know, there have probably been 100 papers that have appeared on the archive since then. And a few of them have taken extended Higgs sectors, and you can, by adding, you know, additional Higgs particles, you can change the ratio, the relationship between the W mass and the Z mass, for instance, by a little bit. So there is room to explain that within extended Higgs sectors. But, you know, even though the recent W mass measurement touts itself as the most accurate measurement of all, there are measurements of that, by the ATLAS and CMS collaborations at the LHC directly, slightly larger error bars, but they are not quite in agreement. And so I think the jury's out about whether that 7 sigma discrepancy from the Tevatron will be the final word or not. So we'll have to see. But the measurements we're showing here don't really care what the W mass is. This is, as I said, this is production mechanisms on the left and then final states on the right. And you're measuring 2 photons, 2 Z's, 2 W's, 2 taus, top quarks in association with Higgs production. Here is vector boson fusion. This is the production of a Higgs boson being Bremsstrahled off a Z boson or a W boson. And down here is production of Higgs bosons in association with top quarks. But okay, so those are all the channels, and then here are the observations, and then this graph has been assembled so that you can see the cross section times the branching ratio into the Higgs boson, observed divided by what it's predicted in the standard model. And if the standard model were correct, all this data should line up around 1, and it does a pretty good job. I've highlighted here the fact that Atlas claims that the p-value of this data is 79%, confirming, well, consistent with the standard model predictions. So that's what Atlas shows. And then CMS has a similar plot, but it's a little older. But their gee-whiz plot that they like to show, although Atlas shows a similar plot as well, plots the data where you see the inferred coupling of the Higgs boson to the various particles, top quark Z, W, bottom tau. And more recently, there's evidence for couplings to the muon. And if the standard model were correct, all this data should lie along this line. This is just saying that the Higgs couplings to particles are proportional to the mass. Technically speaking, for fermions, proportional to the mass, for bosons, proportional to the squared mass. But in any case, that's taken into account in this plot. And then you see this very nice linear prediction, and the data lines up quite well. Okay. Oops. So that's all standard model physics. And so you might want to say, okay, we've once again proven that the standard model is king and time to go home. On the other hand, if you think about the structure of the standard model itself, it's not a theory that you would say is of minimal form. The most trivial example of that is the standard model involves 3 generations of quarks and leptons, not 1. The famous remark by I. Rabi back in 1936 when the muon was discovered was, who ordered that? That was the first evidence of beyond 1 generation of fermions. The gauge group of the standard model is certainly not of minimal form. So why should the scalar sector be of minimal form? Why should there only be 1 Higgs boson? It seems that if you were just wanted to replicate history here, you would expect the scalar sector of the standard model to be a little more complicated. So this leads me to trying to motivate why one might want to extend the Higgs sector. And well, there are quite a number of theoretical motivations for doing so. If you're interested in trying to understand the origin of baryogenesis, you need to have a first order electroweak phase transition. This is something that could have happened in the standard model with different parameters, but does not happen when you have a Higgs boson whose mass is 125 GeV. So if you want to use some of the well-known mechanisms for producing baryons in the early universe, or basically destroying the symmetry between baryons and antibaryons, you really want to modify the standard model in some way to produce an electroweak phase transition that's first order. Extended Higgs sectors can enhance vacuum stability. This comment follows from a variety of papers that were published soon after the discovery of the Higgs boson that pointed out that if you just take the standard model and extrapolate to very high energies, you would discover a second, deeper vacuum than the electroweak vacuum at some very large energy scale, but below the Planck scale. if this were true, then our current vacuum would be unstable. Lucky for us that when you do the calculation, you discover that our vacuum is metastable and has a lifetime many orders of magnitude longer than the age of the universe. But nevertheless, this does make certain people nervous, and they would feel a little bit perhaps more comfortable if the electric vacuum was actually the lowest vacuum. And you can do that by, of course, adding new physics beyond the standard model at some high scale. Extended Higgs sectors is one way to do that. Another motivation for extended Higgs sectors, they can provide a dark matter candidate. The dark matter, if it's due to a particle, has to be some particle that lies beyond the standard model. There are many theories of physics beyond the standard model that can provide such candidates. Extended Higgs sectors are one of many. Extended Higgs sectors have been used to provide a solution to the strong CP problem via the axion. And finally, to honor O'Rafferty, I can't help but mention the minimal supersymmetric extension of the standard model as one of the most popular and explored models of physics beyond the standard model that try to explain another issue of Higgs physics that I will not explain today, which is how do you understand the naturalness of the electric symmetry breaking scale, but within the context of supersymmetric extensions of the standard model. In fact, you require additional scalar Higgs states. Otherwise, your theory would be anomalous. So plenty of theoretical motivation for extended Higgs sectors. Just to show some picture to show you how you might use the Higgs sector to get a new dark matter candidate. If you extend the Higgs sector to the 2 Higgs doublet model, and that second Higgs doublet, if you propose a new symmetry, a discrete Z2 symmetry, and have that second Higgs doublet to be odd under that symmetry, but all other matter, fermions, gauge bosons, the first Higgs doublet, those are even under the Z2 symmetry, then you have a stable scalar particle from the Z2 odd sector, the lightest of which is called the lightest Z2 odd particle, or LOP, and that could be the dark matter. And I just show you some plots from a paper from 2013 that show you what part of the parameter space exists, which would give you such a particle that would be consistent with the observed dark matter in the universe. So you can see over here, there are regions, maybe they're not incredibly large, but nevertheless they exist, in which this particle can play the role of the dark matter.
And what way is this modeled in a Lagrangian?
Yeah, it's just taking a 2 Higgs doublet model and adjusting the parameters in a certain way. So yeah, it's really easy to write these models. It's called the IDM, or the inert doublet model.
Okay.
And one interesting side note about the inert doublet models, it has a charged Higgs boson, which could enter into loop corrections to our Higgs boson, the one that's been discovered at the LHC, to gamma gamma. So you might get a hint if you were to see a deviation of the predicted decay rate for Higgs to 2 photons. The current data that I've showed you already is, a 10% measurement for Higgs to gamma gamma. So we know that within 10%, we're consistent with the standard model, but these corrections would be expected to be probably an order of magnitude below that. So you would need a fair bit of data, more than we have so far, in order to be sensitive to these loop corrections. But of course, you would be able to produce these particles in pairs, at the Large Hadron Collider. So you might be able to see evidence in that way as well.
Sorry, how on the left, it says you have the upper limits, meaning that the areas that are colored are ruled out?
Well, yeah, I mean, there's if you read the small print, that this tells you they did a scan, and the green points were all the points in the scan, and then they imposed various conditions, and then eventually on the right is what remained after all the the theoretical conditions and experimental conditions were imposed.
Collider-wise as well?
Well, collider-wise and then dark matter-wise, the on the right eventually.
Yeah.
When you impose that you want the lightest Z2i particle to be the dark matter,
Yeah.
then you ended up there.
Yeah, just some of the couplings in the low mass region look a bit large. I mean, like the Higgs to invisible branching ratio, wouldn't that constrain this level?
Yeah, I mean, this was done in 2013. Since then, the Higgs to invisible branching ratio is now more constrained than it was in 2013. So that presumably would shrink the parameter space a little bit more. But as far as I know, their regions still exist.
Mm.
Okay, so this motivates us to consider extended Higgs sectors, but you can't do anything you want. There are quite a number of constraints. So I've listed some of them here. One is the electroweak row parameter is very close to 1. This is the relation between the W and the Z mass in the standard model. And I'll show you a slide coming up telling you what that imposes on the nature of the extended Higgs sector. The second condition is that there better be in your extended Higgs sector one scalar that looks like the standard model, the observed Higgs boson, the LHC. Now, of course, at present, we've only discovered one Higgs boson, and so if you just write down a random extended Higgs sector, you better make sure that it's not in conflict with that statement. In other words, extended Higgs sectors have other Higgs scalars predicted, and you better understand why they haven't been discovered yet. Now, when you extend the Higgs sector, if you just do anything, then models of that type will generate flavor-changing neutral currents mediated by neutral Higgs boson exchange. These are known to be extremely suppressed just by observed data. And so you better make sure your model satisfies that. A random extended Higgs sector will have new sources of CP violation, which have never been observed to this point. In particular, they have implications for electric dipole moments. So one of the most sensitive measurements that exist that haven't been seen yet, that could be generated by new sources of CP violation. And then you can have charged Higgs exchange. If you have charged Higgs bosons in your extended Higgs sector, that could modify predicted standard model processes. Two of my favorites are the decay of a B meson into a D meson and taus, which can be, this occurs in the standard model through W boson decay, but if there are charged Higgs bosons, you can replace the W boson with a charged Higgs boson and generate new contributions to the amplitude. And so the data so far shows that this is more or less consistent with the standard model. Although I should say I chose this one because there is an anomaly by few sigma in the data on this particular decay. Although it turns out that if you took that anomaly seriously, it's probably can't be explained by charged Higgs exchange, but it's certainly sensitive to it. And then beta S gamma, which also significantly constrains the charged Higgs mass and the couplings. So just a word about the row parameter constraint. Here is the definition of the row parameter, at least at tree level. And if you add a weak isospin T and a hypercharge Y Higgs multiplet, in order to maintain this prediction at tree level, you have to satisfy this particular constraint. And you can check that this constraint is satisfied by any singlet charged Higgs and also any doublet Higgs boson with hypercharge 1, of which the standard model is one example. But this suggests that if you don't want to screw up this relation, one of the easiest ways to do that, consistent with the row parameter constraint, is to just replicate the standard model Higgs doublet that you already have. And so the two Higgs doublet model is a simple example of that, where you just add a second Higgs doublet with the same quantum numbers. Now, of course, you could always achieve rho equal 1 by some mysterious fine tuning where you require the sum rule to be equal to 0. If this relation was satisfied, then this would automatically be 0. But if it's not 0, you can still achieve rho equal 1 by summing over all possible multiplets and somehow finding this equal to 0. But let's just say that in all cases, such a relation, if it were to hold without this coefficient being 0 for all cases, it would require some sort of fine tuning. There are examples where it looks like you can make this work with no fine tuning, but then you discover that the symmetries that you've imposed to get this cancellation to occur in the sum are actually only valid at tree level. And the radiative corrections with those symmetries that you used aren't symmetries of the entire model, just of the Higgs sector itself. And so you would get fine tuning when you turned on radiative corrections. So not true for just replicating the standard model Higgs doublet.
Sorry, no, yes, I think Denjo is going to ask the same question. But go ahead, Denjo.
Go ahead. I was just going to ask, the true value of rho is not 1. At least it's not, you have some one loop corrections that you can compute.
Absolutely. So this is just a statement about the tree level version.
And how close to 1 is it when you complete?
When you put radiative corrections in 1 part in 100, roughly speaking.
Oh, they're very small. Okay.
Yeah, they're very small. So this is there's another T which I haven't used here. Sometimes this is called rho equals alpha times T, where alpha is about well, alpha is 1/137, and then that T parameter is defined that incorporates not only tree level effects, but loop level effects. And then you can look at the particle data group for what the latest values of T are, and they're on the percent level. There are other parameters that come along with T, something called S. And by the way, and there's a third parameter called U. And again, you can look at the particle data groups, latest summary of all of particle physics, and they'll show a graph of what's in the ST plane, what is allowed by the data. And again, it's a few percent. And by the way, one of the ways of shifting the W mass so that you account for the latest Tevatron result would be through radiative corrections. Radiative corrections due to to beyond the standard model, because in the standard model won't give you enough.
So then to explain the whatever discrepancy in the W mass, then would you be able to do it with doublets or singlets, scalar?
Yeah, I mean, as I said, there are papers that even within the 2x doublet model, you could generate enough of a shift to explain that.
So that would be at loop level, because at tree level.
Yeah, that's all at loop level.
Yeah,
Absolutely.
but
Yeah.
with a triplet, for example, you could then do it at tree level.
Yes. Yes, if again, that would involve fine tuning now.
Of course.
Extra fine tuning beyond the standard model fine tuning. Okay, so now we come to the question of why is the observed Higgs boson so much resembling that of the standard model? Well, one possibility is there's no extended Higgs sector, that the standard model is the viable low energy effective field theory up till very high energies, and that would explain why the observed Higgs boson behaves like the standard model predicts. But I already gave you a bunch of motivations for why you might want to go beyond that. And so if there is an extended Higgs sector, how would you explain a standard model like Higgs boson? Well, one way of doing it is to have all the other scalars apart from the Higgs boson we've seen, have them all very heavy. Now, how heavy do they have to be? No, it's enough to have all the Higgs bosons above, I don't know, 700-800 GeV, something like that. In that case, their effects on the behavior of the observed Higgs boson would be at the few percent level, which would be consistent with the observed data. This is what's called the decoupling limit. But there's a second way of doing it, which is, say you start out with some scalar interaction eigenstate, which is exactly the standard model Higgs boson. But if there are other scalars in the theory, you could have mixing between that interaction eigenstate and the other scalars. And then there's some mass matrix, which you have to diagonalize. And to get the mass eigenstates of the theory, of which one of them should be the observed Higgs boson. Now, if this mixing, this that I've just mentioned, if it were to be suppressed for some reason, then that neutral scalar whose tree level properties are precisely those of the standard model Higgs boson, then that interaction eigenstate is an approximate mass eigenstate if the mixing is suppressed. That's what's called in the business the Higgs field alignment limit. In some sense, what's happening, and I'll show you in a minute, is that what's being aligned here is the interaction eigenstate that behaves like this, the Higgs boson itself, in field spaces aligned with the direction of the vacuum expectation value. So that's the alignment we're talking about. Again, I'll show you more precisely in a minute. So if that interaction eigenstate is an approximate mass eigenstate due to suppressed mixing, then you will predict a scalar in the model that will behave more or less like the standard model Higgs boson. Now, by the way, the decoupling limit is an example of this because in the decoupling limit, the mixing is suppressed. So decoupling limit is a special case of the Higgs field alignment. So let me now explain how this works in practice in an extended Higgs sector. So since we're okay with doublets and singlets for the row parameter, let me just focus on that, although I'll throw away the singlets in a few slides. But we can include them here in this discussion. So you have some fields, capital phi for the doublets, small phi for the singlets. They gain vacuum expectation values. the observed 246 GeV, which is the square of the vacuum expectation value of the standard model, now gets replaced by the sum of the squares of the vacuum expectation values of the doublet fields. So that's what has to be 246 GeV to explain the Fermi constant of weak interactions. Now I can always take those fields phi and just redefine them by taking arbitrary linear combinations. So one of those linear combinations is this one called H1, and the linear combination is given over here. You can see that. And then I'll define the other fields of the theory to be orthogonal to that. And if you just plug in the vacuum expectation values, you'll see that H1 actually has a vacuum expectation value equal to the full 246 GeV divided by √2 using the normalization that I like to use. All the other Higgs field linear combinations have no vacuum expectation value. So you can always just redefine the scalar fields in this way. And it's very convenient to do so. And this basis of fields is called the Higgs basis. And this is where you get to see the alignment of the with the direction of the vacuum expectation value. So in other words, this H1 here is a interaction eigenstate that behaves exactly like the standard model Higgs boson. And if it were a mass eigenstate also, then it would look to you exactly like the Higgs boson of the standard model. And technically speaking, that would be real √2 times the real part of H10, subtract off the vacuum expectation value. That's the state that if it were a mass eigenstate, then the tree level couplings would all be exactly as they are in the standard model. So that's called the exact alignment limit.
Sorry, how you say if it is a mass eigenstate?
Yes, so that this H1 could, if you write out the potential, can mix with H2, H3, etc. So you have to determine the mass eigenstate, you have to work out the squared mass matrix and diagonalize it. And if there's mixing of H1 into these other things, then the mass eigenstates of that theory would not resemble the standard model.
So I'm thinking like in a 2 Higgs doublet model, when you go to the Higgs basis, then isn't H1, no, it's not necessarily the H of standard model. I see, yeah.
Yeah, I'll show you in a minute or two this explicitly in the 2 Higgs doublet model. So the question is, can we understand? LHC is telling us that there's one scalar state that resembles the standard model Higgs boson. Can we understand this in the setup that I have here, which would mean we'd have to understand why is the alignment limit very close to exact. That's what the experiment tells us. So and in particular, is there a natural explanation for this? Now, naturalness is a loaded term. There's the whole question about the standard model Higgs boson itself in the context of embedding the standard model in a more complete theory, an ultraviolet complete theory with a very large energy scale, say the Planck scale. It's very puzzling why the electroweak scale is so much less than the Planck scale. And so that's the naturalness of the standard model Higgs boson mass itself. I'm not going to address that question here. We'll have to put that aside for some other day. Supersymmetry is one possible explanation. There are others, but again, let's put that aside. Beyond that, if you accept the existence of the electroweak scale, you can still ask, is it natural to have a standard model like Higgs boson in that extended Higgs sector? Now, an example of what I would consider a natural explanation is the decoupling limit, because in the decoupling limit, you just have additional scalar states that are quite heavy. In fact, naturalness would suggest that scalar states like to be heavy, to be at the highest possible scale possible. So from that point of view, the decoupling limit is a perfectly viable explanation for why the observed Higgs boson is standard model-like. But you know, if the extra scalars are too heavy, we're not going to discover them at the LHC. Perhaps they're even too heavy to be produced, and then we'll still be left with the mystery. So the central question in this talk is whether you can have both a standard model like Higgs boson and then additional scalars that you might actually discover experimentally in future experiments. And that means, can we understand the possibility of approximate Higgs alignment, but without decoupling? Okay, so that's the question. And I just want to remind you that naturalness, the way we understand it in modern particle physics, was explained very beautifully by 't Hooft in the late 1970s. And the way he stated this is that you would have naturalness of a parameter which is small. If you were to set that parameter equal to 0, you would find that the symmetry of your theory would be larger, extended. An example of this is the electron mass is natural, because if you set the electron mass to 0, then your theory has a chiral symmetry, which is a symmetry that's larger than the one that existed before you set the mass equal to 0. And so then the chiral symmetry is broken by the mass term, but that mass term is a soft symmetry breaking term. And so that's the form of naturalness that I will pursue in this talk, that I will have some symmetries, but those symmetries, I will allow them to be softly broken. Okay, so how do we achieve Higgs field alignment in the 2 Higgs double model? So let's just take a closer look. So we focus on a model with just 2 Higgs doublets. I'll go to the Higgs basis, and here is what previously was called H1. This is the one with all the vacuum expectation value. H2 has no vacuum expectation value. And then we say that we have exact alignment if the real part of this scalar here, once you subtract off the vacuum expectation value, is a mass eigenstate. But as I asserted, that in general, you would have mixing between this state. Now, by the way, the imaginary part of this state is actually the Goldstone boson that gets absorbed due to the Higgs mechanism by the Z, and the Z becomes massive. So that Goldstone boson is 0 mass and independent of whether there's mixing or not. But what can mix is the real part of this field here with the real and the imaginary part of this field here. And so you have to write a mass matrix, and there are 3 degrees of freedom there once you've eliminated the Goldstone boson. So you're talking about a 3x3 mass matrix. But just so that I can illuminate the mechanism here, I will make an additional assumption that I don't have to make, but it's just made for simplicity, namely CP violation. I'm going to assume no CP violation in the Higgs potential, and therefore the real part of H1 will only be able to mix with the real part of H2. And so now I'll only have to diagonalize a 2x2 mass matrix. Before I do that, let me show you what the scalar potential looks like in the Higgs basis. Here it is. There are 3 squared mass terms called y1, y2, y3, and 7 dimensionless couplings, which I call z1 through z7. And if you minimize the scalar potential, you get some very simple equations here. And just by looking at this, you can see that you would get exact Higgs alignment if Z6, that's why I've highlighted these terms in red, is equal to 0. And if Z6 is equal to 0, then Y3 is equal to 0 by the minimum condition. And you can see that this yields no mixing between the real part of H1 and H2 in the mass matrix, because H1 is the one that has the vacuum expectation value, H2 does not. So when you do the shift, H1 goes to H1 plus V over root 2. The only way to get a quadratic mixing between H1 and H2 is in an H1 dagger H2 term, like so. So if I now write out what that mass mixing looks like in the approximation of a CP conserving Higgs double model, where I only have to look at a 2x2 mass matrix, you get a mass matrix that looks like this, and the off-diagonal terms, that's the mixing, and as promised, that's proportional to Z6. So that if Z6 were exactly equal to 0, then I would have exact Higgs alignment. And by staring at this mass matrix, you can see the decoupling limit. So the decoupling limit is one where there's a squared mass parameter here called MA, which is large. So in that case, it doesn't matter. Z6 is an order 1 number, but doesn't matter because once this is large, just by simple perturbative analysis, the effect on this 1,1 element, which would govern the mass eigenstate itself, the corrections to that would be of order Z6 V squared over MA squared. So if MA squared is much larger than V squared, then the effect is suppressed.
Do you have to do anything special with the interaction terms? Yeah, I think you just showed us the quadratic terms.
I showed you the quartic. These are quartic. The Z's are the quartic terms.
Oh, the quartic ones. And if I look at this potential, I just have to make y1 negative, is it?
Yeah, there are conditions. Yeah, so in this minimum, exactly. So Z1 actually must be greater than 0 for stability. So this tells you that y1 has to be negative.
Okay.
The minimum condition. Yeah.
And that looks natural when I go to the original basis.
Well, in the original basis, actually, it's more complicated, but yes, in the original basis, there's a little 2x2 mass matrix, and the determinant has to be less than 0, for instance.
Okay.
But in this basis, it's much simpler. It's just y1 has to be negative. Yeah.
Okay.
Okay, so looking at the 2x2 mass matrix, you see the decoupling limit just having MA large. But the other way to get the approximate Higgs alignment is to have Z6 small. Z6 equals 0 would be exact Higgs alignment. Z6 small would be approximate Higgs alignment. And in fact, you see that if Z6 is small, then MA can be of order V. MA turns out to be the mass of the CP odd scalar here in the CP conserving case. And so this would allow the additional Higgs bosons of the model to be not that much heavier than the observed Higgs boson itself and still maintain approximate alignment because E6 is very small. And so one of the questions that I'll address is the alignment without decoupling is the topic of interest for this talk, because I want to explain a world where the observed Higgs boson is standard model-like, and yet we have a chance to discover new scalars at the Large Hadron Collider. So that would be this case.
Sorry, you haven't said anything about Z7 yet. So
and I won't say anything about Z7.
yeah, so if Z6 is really small, but Z7 is non-zero, we're still in the alignment without decoupling
Correct.
limit.
Correct.
Um, but,
Z7 doesn't affect the mass matrix at all.
but would that be a natural choice?
Well, bear with me, we'll see. Because the symmetries that I'm going to eventually impose will impose some constraints. Now, just to make contact with some data, here's the diagonalization of the states. So this is here where the interaction eigenstates, here are the mass eigenstates. Little h in this notation is going to be the lighter of the two Higgs bosons. This will probably be the standard model like Higgs boson. There's a mixing angle, which in the Higgs basis turns out to be something that in the literature is called beta minus alpha. And we need not go into the explanation of why there are two angles. I mean, if you're curious, it's because normally people diagonalize the mass matrix in the original basis, not in the Higgs basis. And in the original basis, the diagonalization angle is alpha, and then there's a parameter beta that's related to the ratio of the two vacuum excitation values. But in the Higgs basis, these two parameters come together, and it's just the difference of the two parameters that's relevant. And so you see, just looking at this, this purplish object here, that's the interaction eigenstate that's exactly standard model like. And so if little h is to be standard model like, then cosine beta minus alpha beta be very small, close to 0. By the way, if the heavier of the two Higgs scalars were standard model like, then you'd want sine beta minus alpha to be very small. Probably, although it is possible that there is a lighter scalar that has not yet been discovered. So you can't quite rule out the possibility that it's capital H, it's the standard, the observed standard model like Higgs boson. But most of the parameter space, it's the little h. So that will tell you that cosine beta minus alpha should be small. Here's the formula so that you can see from, this is an exact formula, this is an approximate formula, but you see two ways of making cosine beta minus alpha very small, either Z6 close to 0 or M capital H is very large. And those are the two cases I've already discussed, either the decoupling limit or alignment without decoupling. And so what does the data tell us? So this is, again, from Atlas, because they have the nicest, most up-to-date graphs. This shows you plotting cosine beta minus alpha. Now, they plotted versus a parameter tan beta. They're in a particular type of model called either type 1 or type 2. This has to do with the Yukawa couplings of the model. That's not, I don't want to get into that story here. The lesson to be learned is that the allowed data is only the region that's not colored. So the whitish region. And so what this is telling you is that cosine beta minus alpha, if it's not 0, is pretty small. And so that's just another way of saying that the observed Higgs boson is standard model like.
Sorry, Howie, why aren't these graphs symmetrical?
Yeah, I was thinking, I can't give you an answer to that off the top of my head.
Okay.
Yeah, I've noticed that too, and I don't have a quick answer for you there.
Okay.
But the important point for us is not that. The important point is that cosine beta minus alpha is pretty small.
Mm-hmm.
Okay, so how can we achieve exact Higgs alignment in the two Higgs doublet model? Well, it turns out there's a very simple symmetry you can impose. I've already mentioned this, the inert doublet model, where you add a second Higgs doublet that's Z2 odd, everything else is Z2 even. And if you posit that this Z2 symmetry is an exact symmetry, well, then you have exact Higgs alignment. You have Z6 equals 0, in fact, exactly at tree level. You could get deviations from standard model-like behavior at the loop level. And I already mentioned this to you in the inert doublet model. You can have the charged Higgs boson giving you small corrections to the observed standard model Higgs boson decay to 2 gammas. But those corrections are quite small. And so this is a completely viable explanation and a natural explanation for having an extended Higgs sector with a standard model like Higgs boson. Now, what this would predict is exact Higgs alignment, although exact Higgs alignment is a tree level statement, but nevertheless, it would say that the measured couplings of the Higgs boson should be exactly those of the standard model up to small radiative corrections. And those radiative corrections are, percent level or less. And so if that's the way nature is, you're not going to see any evidence at the LHC in the next 20 years for any deviations from standard model like Higgs behavior. This is what this would propose, with the possible exception of gamma gamma, if you were able to measure the Higgs to gamma gamma rate, because that's already at the loop level. Then standard model and standard model contributions and new physics contributions are coming in at the same level there. So then you have a shot at seeing some evidence. But in this case, the predicted values of the couplings would not deviate experimentally.
Sorry, I have a silly question. So when we impose a symmetry, we expect it to be respected by the loop contributions as well, right?
Yes, indeed. And that symmetry is, so when you have a charged Higgs loop, every vertex involves a pair of charged Higgs bosons. So a pair of Z-odd particles can couple to Z2 even particles.
Yeah, so when you say the Higgs alignment limit is a tree level argument, it is, but not in the IDM case, because there's a Z2 symmetry imposed.
Well, yes, yes. Okay, so my hope is if you have alignment without decoupling, that it's only proximate, so that eventually you will see deviations as you make more and more precise measurements of the observed Higgs boson couplings at the LHC. So we're at the 10 to 20% level now. In 10 years or so, you'll be below the 5% level. In some channels, you might even get closer to a % level. Maybe someday, maybe not in my lifetime, that we'll have a Higgs factory built that will be able to probe these couplings at the 1% level and lower. And so my hope is that eventually experiment will reveal small deviations from standard model Higgs couplings. If that were to be realized experimentally, then you would say you're in the approximate Higgs mass, approximate Higgs alignment limit, and without decoupling. And that's not possible in the IDM. In the IDM, you can't break the symmetry softly. You're stuck with exact alignment in the IDM. The IDM is too good for that. So I'm going to be interested in the possibility of having a symmetry reason for approximate Higgs alignment. So I'm going to allow for soft symmetry breaking terms to eventually, hopefully, provide the possibility of observed deviations in experiments.
Sorry, Howie, may I ask another silly question?
Yes.
Why is the soft breaking term called soft breaking?
Well, it's distinguished from hard breaking. So hard breaking would, if I take my symmetry, impose it on the Lagrangian, and then add hard symmetry breaking, namely dimension 4 terms in the Lagrangian, then there's no remnant of the symmetry left.
Yeah, I mean, so I wouldn't call that a broken symmetry. I just would say there isn't a symmetry. Yeah.
Well, when you have soft symmetry breaking, there's still no symmetry technically.
Yeah.
But the point is, because soft means that at very high energies, you don't see the symmetry breaking.
Okay.
So
Yeah.
that's all. Okay, so we need to talk about symmetries in the 2x doublet model. What possible symmetries can I add? An example was that Z2 symmetry that the IDM uses. So here's the most general potential of the 2x doublet model, now written in the original basis. I want to make sure that my gauge covariant kinetic energy terms respect any symmetry that I propose. And if you require that the gauge covariant kinetic energy terms are symmetric, that reduces the possible symmetries under discussion to U2. Namely, phi goes to U phi, where U is a 2x2 matrix over the two possible Higgs flavors, 1 and 2 here. And so the possible symmetries we can impose on the 2x doublet model would be either U2 or subgroups of U2. Z2, of course, is a subgroup of U2, kind of one of the simplest ones. And so these symmetries have been, all possible symmetries have been figured out. And I've made a list just to show you what they are. Z2, here's one of them. Pi 2, where you interchange phi 1 and phi 2 is another one. We'll see in a minute that these two symmetries are actually not distinct. There's the U1 Peccei-Quinn symmetry, which is a phase symmetry. There's SO3, which is kind of like the U2 symmetry, but I've taken out the U1Y hybrid charge, which is exactly satisfied just from the gauge symmetry. But these are global symmetries that I'm talking about that I'm imposing on the Higgs potential. There are also CP symmetries that involve the complex conjugate. The simplest one, called GCP1, is the standard one that we all know, but there are other interesting versions of generalized CP transformations where you do some more things. And if I take those symmetries that I've just written down and impose them on the scalar potential, I get restrictions. And here's a table that shows you what those restrictions are. Well, what's kind of amazing is that even though Z2 and pi 2 look very different, remember, this is in a particular scalar field basis. And it turns out that if I change the basis just by redefining the fields, I can turn a Z2 symmetry into a pi 2 symmetry. So that's the color coding. And it turns out that these two green ones are equivalent as well by a change in basis. And these orange ones are also equivalent when I change the basis. So in fact, there's 1, 2, 3, 4. There turn out to be just 5 and then 6, just the CP symmetry. That's the complete list of all possible symmetries that are physically distinct that you can add to the 2x doublet model. And I want to focus now on one particular symmetry, which is this GCP2 here. And it turns out that that leads us to what my colleague dubbed the exceptional region of the 2x doublet model parameter space, or ERPS is the acronym. And so if you go back to this chart, you see that it says that lambda 7 here must be minus lambda 6. And M11 squared is equal to M22 squared. So that's the condition here. And that greatly simplifies the model. In fact, reduces the original two-exponent model had 11 degrees of freedom. Now we're down to 5 degrees of freedom. Now, if I allow the symmetry to be softly broken, then I throw away the constraints on the squared mass terms, and then I'm just have lambda 1 equal lambda 2, lambda 7 equal minus lambda 6. That's still fewer degrees of freedom than the general case. And then a remarkable theorem, and you can ask me after the talk about how to prove this, because there's a very slick way of doing this, is that if lambda 1 is equal to lambda 2 and lambda 7 equals minus lambda 6, then I can change the scalar field basis to set lambda 6 equal lambda 7 equals 0. And if you go back to this slide here, that just, that's just saying that GCP2 in a different basis is equivalent to imposing both these two symmetries, E2 and Pi2, simultaneously. As you can see here, that sets lambda 6 equal lambda 7 equals 0. It sets lambda 5 real. Okay. Let me skip there are lots of interesting features about this parameter regime, but I think I'm going to skip this for time because I want to get to the main points of the talk, which is I want to explain now Higgs alignment without decoupling due to a symmetry, which I'll allow to be softly broken. And so here's the key point, that if I go to the Higgs basis, then I can get an expression for Y3 in terms of the parameters of the original model. In this case, M11 squared, M22 squared, M12 squared, and beta, where beta, remember, is the tan beta is the ratio of the two vacuum excitation values, or to put it here, in the original basis, phi1 and phi2 have vacuum excitation values parameterized by actually beta and then a phase in general, xi. And then you can work out what that implies for the Higgs basis parameter Y3. And you get this formula here that I've highlighted. And the one thing you immediately notice is that if I set M11 squared equal M22 squared and M12 squared equals 0, then Y3 is equal to 0. And I already showed you that there was a scalar potential minimum condition in the Higgs basis that said Y3 was proportional to Z6. And so if Y3 is equal to 0, then Z6 is equal to 0, and then I have exact Higgs alignment. And so if I have a symmetry reason for M11 squared equal M22 squared and M12 squared equals 0, then I have a symmetry reason for exact Higgs alignment. And that's what's going on here. So here's the list of symmetries that I've imposed. And these are the exceptional regions of the parameter space. And you see that in all these cases, M11 squared is equal to M22 squared, M12 squared is equal to 0. So every one of these symmetries, if they were exact, gives you exact Higgs alignment. And this is a symmetry reason for Higgs alignment. And now I'm going to allow myself to break that symmetry softly by now allowing M11 squared not to be equal to M22 squared and M12 squared not to be equal to 0, but keeping the rest. And that will be examples of approximate Higgs alignment. Z6 now will no longer be 0, perhaps, but it can be naturally small. And so here I made a table of all the possible ways that Z6 could be not equal to 0, but naturally small by looking at those symmetries and just looking at various parts of the parameter space. And so you needn't look at this table all that carefully. Just the message of this table is that you can break the symmetry softly and have Z6 very small. And so that's what I want to do. So question, have we succeeded? have we now achieved natural approximate Higgs alignment? And the answer to it is not quite, because so far all I've done is I've shown you what the relevant symmetry is in the scalar sector itself. Now this is a symmetry of the bosonic part of the model. But when I couple to fermions, now I have to discuss how the fermions behave under the symmetry. So the question is, can I extend the symmetry to the fermionic sector? And in particular, GCP2, which was sort of what was called the exceptional region of the parameter space, can I extend the Yukawa interactions to respect GCP2 or some of the others, which are even more symmetric? And unfortunately, the answer is no. There was an attempt to do this back in 2010. It failed. And so at this point, it looks like we've lost, in some sense, that if we want a symmetry explanation for Higgs alignment, the only way to do that is in an inert doublet model setup. Which you cannot break softly. So, and here I wanted to break the symmetry softly to have approximate Higgs alignment, not exact Higgs alignment at tree level.
So sorry, Howie, when you say you got, it didn't work, you mean you couldn't produce the CKM matrix, or?
Correct.
Oh, I see.
Yeah, I mean, if you wanted to do if you wanted to extend this into the Yukawa sector, Yukawa sector involves the interaction of a single Higgs boson with a pair of fermions. Now, under these symmetries, the Higgs boson itself, the scalar field transforms. Yeah. So you have to have the fermions transform. Well, how the only degree of freedom you really have is in generation. So you would have to have some symmetry among the generations. And when you do this, is what Ferrer and Silva tried to do. It just wasn't consistent with the observed CKM matrix and the masses of the quarks, et cetera, et cetera.
If I understood correctly, you were restricting yourself to global symmetries.
Yes, these are global symmetries.
And some of them look like they had the potential to be gauged.
Well, of that U2 global symmetry, which is where we started with, there's a U1 sitting inside of it, which is hypercharged, which is gauged. But we're not gauging the rest of it. Yes, you could. That would mean extending the standard model gauge group beyond SU3 cross SU2 cross U1. So,
but it's extending it into this extended sector.
Well, the way I would look at it is you extend the gauge group, and then now you have to say you need scalar particles to generate masses for not only the W and Z, but say your new U1 or whatever. And then you'd have to figure out what scalar content you want to use.
But
so
you have lots of scalar content there that you
have lots of scalar content. So that would be a direction to go, possibly. And I haven't looked into that direction. So yes, I've been sticking with the standard model gauge group, and that's been an assumption all along. But yeah, that would be another approach. So the point I want to make here is, so at this point, you either give up or you try to get clever. And so my colleagues and I tried to get clever, and we said, okay, so you can't extend this symmetry into the Yukawa sector as it exists in the standard model. So let's extend the standard model a little bit. And so our idea was to introduce additional fermions into the theory, which would allow us to extend our, say, GCP2 or GCP3 symmetries to the Yukawa sector in a way that wasn't available to Ferrer and Silva. And so that's what I'm going to do in the final part of my talk. And so as an example, I'm going to take a GCP3 symmetric scalar potential, but I'm going to realize that in another basis as U1 cross pi 2. So let me just go back just to show you what the symmetries we're talking about here. So here GCP3 in another basis is U1 cross pi 2. So U1 cross pi 2, this U1 is the Peche-Quinn U1. So it sets lambda 5 equal to 0 in addition to lambda 6. So that's the one additional feature of this symmetry. So I'm going to set lambda 5, lambda 6, and lambda 7 equals 0, and then I'll softly break it by allowing m11 squared not equal to m22 squared, m12 squared not equal to 0. That's what we're going to impose on the scalar part, and now we want to extend that to the fermions. And so I'm going to add to my standard model fermions a vector-like, some vector-like particles. Let's call it, this will be like a partner of the top quark. U is an up-type quark, so here I'm just focusing on one generation. But in this case, we can extend this to multiple generations because we can do everything within the confines of one generation. These symmetries will be generation independent. So for you, think of that as the top quark, and then this is a top partner. And the hypercharges are given like so. So these are vector-like singlet two-component fermions. And so here's a possible Yukawa interaction that's consistent with, sorry, now under the pi 2 and the U1, these are the transformation laws. And so here's what I'll posit. For pi 2 changes a little u bar into a capital U bar, for instance, and a capital U bar into a little u bar, and it leaves the capital U alone. The U1 will take the phase that phi 1 and phi 2 experience, and it doesn't affect the ordinary quarks, but the vector-like quarks that will have this phase. And when I posit those symmetries, here is possible Yukawa interactions of the ordinary quarks with the vector-like quarks, which is symmetric under this U1 cross pi 2. Okay, so at this point, I've respected the symmetry, but it's not phenomenological viable because I've introduced vector-like fermions. They would gain mass through mixing, but they would be small. They would be electroweak in size. No vector-like fermions have been seen at the Large Hadron Collider. There are bounds, and they're actually quite strict. They should be above the TeV in most cases. And so it's not enough to have this Yukawa interaction, but here's the point. The point is I can add a mass term. And this only softly breaks the symmetry. And so this plays within the rules that I've set up, that I want to be able to allow for my symmetry to explain Higgs alignment, but I want to break it softly to explain why the Higgs alignment would be only approximate. And so here I could introduce mass terms because these are vector-like particles here. And these break the U1 and the Z2 symmetries, but only softly because these are dimension 3 terms. Now, this is an effective field theory. There's a cutoff to this theory, some scale lambda, which will lie, we imagine, in the multi-TeV range. But below that scale, this effective theory has these symmetries. And so you can estimate by putting in the soft breaking terms here. They will then generate corrections to the exact symmetry we had before. These exact symmetries set m11 squared equal to m22 squared and m12 squared equals 0. So now that we've broken the symmetry, we will generate corrections to that. And here are some diagrams to show you what you get. So you will get a splitting of m11 squared and m22 squared. That are only logarithmically sensitive to the cutoff scale, which is why this is approximately natural, because this log can't be too large as long as lambda is not, I mean, you can't put lambda equal to Planck mass here. So here, the ultraviolet completion of this theory would have to be roughly at 10 TeV or something like that. But certainly possible within what we know experimentally. And so you generate from these graphs a delta m squared, and you also generate an m12 squared. Again, you get a term that's logarithmic, and then there's also a threshold correction that you can get as well. And so my collaborators and I took this theory, we generated the delta m squared and m12 squared, and now we can work out all the properties of the Higgs sector and see if we can be in a regime of approximate Higgs alignment. And so we chose, just to be specific, our cutoff scale to be such that the log of lambda over m is 3. M here is going to be a parameter of order TeV. And then there's mixing. So I can get mixing within the vector-like top, between the ordinary tops and the vector-like tops. I can get mixing, and there's a parameter called, depending on the size of these two mass parameters here. So tan gamma is going to be defined at that ratio. And we'll look at that parameter can't be particularly large. We'll look at two cases, 0.1 and 0.3. And then we impose various conditions and we scan the parameter space. So in fact, we wanted to make sure the vector-like top quark masses respected the bounds of LHC. So in fact, we chose our vector-like top quark masses to be above 1.5 TeV. The mixing is constrained. There are flavor constraints. And we wanted to keep the fine tuning small because we want this to be in a natural explanation. Because eventually, if lambda itself was if the cutoff were too large, then you would just end up having fine tuning to explain all this. And so I'll finish off the talk by showing you some plots of some scans we did. This just shows you that in this region, in this colored region, we have where we kept the fine tuning to be at worst case scenario to be 5%. So not too bad. That we were consistent with the observed standard model Higgs properties in the regions of parameter space that I've shown you. And you see that you have values of MA, the CP-odd Higgs boson of the model, below 500 GeV comfortably. So this would tell you that this is a setup in which you have approximate Higgs alignment explaining the observed Higgs boson couplings at the LHC, where you can have additional scalar states that are in the realm of the LHC that you might discover in future running, say below 500 GeV. We haven't discovered these yet, but we haven't ruled out either large fractions of this parameter space. This has already been taken into account in what we're showing you here. And so what would this tell you? This would tell you that if we were to discover new scalar states in these regions of the parameter space at the LHC in the future, then One possible explanation for this would be the existence of new vector-like fermions with masses maybe between 1.5 and 2 TeV, something like that. So, what are the take-home messages from this talk? If an extended Higgs sector with additional light scalars exists, then we need to understand why the observed Higgs boson stand are not alike. Evidence for additional Higgs scalars will emerge either if you discover new scalar states at the LHC in the next 5 to 10 years, or if you discover deviations from the Higgs couplings. Remember, we're only at the 10% level now experimentally. It's still possible that deviations will emerge as the data becomes more precise.
Sorry to interrupt, but I'm going to have to rush out in around 4 minutes. So I'm going to leave you continue, but I'm going to stop the recording in about 1 minute.
Okay, well, this is the last slide, so we're about done.
And you can continue with questions, but unfortunately I won't be.
Okay, no problem. So as I said, in the case of the IDM, which is one way to realize this, the inert doublet model, the deviations from the Higgs couplings will be incredibly small. They're radiatively induced. But if you discover additional Higgs scalars, and if you find small deviation of the Higgs couplings from standard model behavior, then a symmetry-based explanation is the most likely in our view. And at least in the model I presented to you at the end of this talk, one possible explanation for this would be additional new physics in the Yukawa sector that would involve top quark fermionic partners, and perhaps partners to the other quarks and leptons. So that's
Thank you very much. Thank you very much. I'm stopping the recording and rushing out of here before the alarm goes off. Thank you. And I'm passing over the, yes.